the future, which is why there's no completeness proof for these, because new techniques could be developed in the future to define these various variables. So here's kind of an overview of how the 8 are organized that we'll go into in a second. The first one on top is the history duration, which basically says how long has the model been around. I'm sorry, the system's been around. We get into the capability storage of the system, the actual events, and the abstract capabilities and abstract events and states. This is my lesson to remove all these animations for the defense on Friday. This is lesson number 1. So the history duration category is the first one we'll address. And this is actually one of the most basic and simple ones, and one that's actually not really done formally. But there's a set T. We had all of these functions that were mapping a time to a state, or a time to an event, or a time to the devices that were connected. So we had this notion of a set T that basically defines what times does this computer exist and have a history. This category basically defines what times they have a history. Well, if we have the computer at the current time, we basically know it exists now. So the real problem is basically determine when the history of this computer started. That's really what we care about. And actually, even more practically, all we really care about is did the computer exist during the times being investigated? You know, if the computer was made last week and the crime was 2 years ago, it's probably not going to have, evidence from events and states 2 years ago because it didn't exist. So the basic examples for determining these types of things are looking at the manufacture date of the computer, looking at the OS installation date to find out if it existed at that time, looking at the earliest modified access or change times on a system to see if we can get a reference for when the system was created or used. All these are kind of vague and fuzzy and not really accurate, in that we can completely wipe a hard drive, lose all notion of time, and then our earliest time is really 5 years after it was first used. So all of these things, there's no real concrete way to identify the exact date the system's been used, but this is kind of the general goal of these techniques. Second category we're working with is the primitive storage capabilities. So the first category is basically what times does this exist. Now we need to define basically our set Q and our finite state machine definition, which is the set of possible states at each time. So all we're going to do with this is basically define which storage devices we have and what their possible states are at each time and when they're connected. So to define the capabilities of each device, we can basically do this with some kind of hard disk spec. If we have the model number on the disk itself, we can find out that it's, got this many sectors, this sector's this size. We can easily figure out what the actual capabilities of it are. There's queries we can run on it to have it return how big it is and what its sizes are. We won't get into that now, but it's possible for devices to lie to you, basically, if they've been modified by the person that's attacked them. So, the reliability of all these are in question in terms of what you can trust and what you can't trust, since again, these are all indirect observations. But these are all approaches that can be used to actually define these various things. To determine which ones are connected to the system at what time, though, we have to rely on various log files that say this hard disk was plugged in at this time, which usually don't exist, quite honestly. I mean, some Unix systems may have a log that says this model number was on their boot up time, but not all systems have that same out of logging. If you put a USB drive in, you may not have a log record of it being plugged in or not. So a lot of times this is kind of a fuzzy process of trying to figure out when each device is actually connected to the system. And again, you could use MAC times to determine when activity occurred on the disk or the storage location. But again, it's not really a strong, definite reference or resource to determining when they're all connected. The third category, the previous category basically defined the storage capabilities, now we can define the actual event capabilities of the system. So again, we actually examine the event devices, find out what events they can cause, what their state change functions are, and then try and determine which ones are connected at each time. And the way we do this is basically by specs of the processor, querying the processor to see if it returns the list of commands, and then logs that, to find out when they're connected. We may use logs again to find out when they're connected. In practice, this is basically never done, pretty much because primitive level events are, again, as I said, pretty much useless for investigation to find out when the add command was used. So there's really no need to worry about enumerating all the primitive level events or identifying, which their actual state change functions and such things. But this is, again, in the formal categories of things, this could be done in the future if this is deemed to be a necessary part of the investigation. But even more so than with the primitive storage stuff category, there's really no logs at all that record what event devices exist, the CPU ID or any of those kind of devices. So even if that was required, there's very little history about when those were connected to the system each time. I don't get this at all. Okay, so after we've defined the time of the system, we define the capabilities of the system, or what we think are the capabilities of the system at each time. We can then start to define what the actual states and events were. And this is basically, we define what we infer to be the actual states that occurred at a given time and what events occurred. So examples of doing this basically is from directly observed states. So I can directly observe the state of the computer monitor, if you will, or some kind of driver in this, because I can see the actual screen on there. So I can define the state of the controller card of this video monitor because I can directly observe it. I can also, through indirect observations, also define other states in the process of going through all of these various things. Can't see it on my own screen here. Some other ways of going about doing this are event reconstruction and construction. So if we look at this next slide here, this kind of shows the directions we're talking about here. So we have various ways that actually aren't addressed in this. We can define a specific state at a given time. And then with reconstruction, this middle one here, we basically start with a known state, a given state, and we consider what the previous event was, and therefore what the previous state was. And with this, we can start with our known state and basically work backwards and go through and try and figure out the history of the system. Conversely, we can do a construction method, basically start with one state, make an hypothesis about what the following event and state were, and move on from there. It's kind of out of the scope of this, but the reconstruction is the much more common method of doing this. But again, at the primitive levels, this still isn't really a common technique. But this is the basic concepts of how we would go about defining the various primitive states and events if we needed to. So at the abstract level, we have four more categories that we're addressing here. This one is impossible, so it's not really much point discussing it, but here's the main concept. So the main concept is in the formal model, in the discussion, we define what layers of abstraction exist on the system. Basically, these layers are based on, as I said before, how the program was actually developed and constructed and programmed. Whether there was, how many layers of abstraction there were in the development process, which is kind of based on how big the program is. So this category would define the set L in the model, which represents all the various levels of abstraction. To define this would basically require the investigator or someone to interview or somehow determine all of the program development processes that were involved with developing all programs on the system to find out what layers of abstraction actually exist. It's not going to happen, quite honestly.